Once again, very good evening, and it's a pleasure to meet you all again for another session on quantitative structure activity relationships, which is an interesting topic, and it dates back 1960s. Okay, so what is QSAR, as it's popularly known as? Okay, so we already know what is drug design. So basically, drug design, we are trying to develop drug molecules for a specific receptor or target. And in that, computer-aided methods play a vital role in the early stages, at least. And even because these experimental methods takes, say, are time-consuming and as well as expensive. And we are learning various methods. So one very crucial one is molecular docking, where we assess the binding affinity or the efficiency of a drug molecule and its interaction with the receptor. Okay, so that's where everything starts. That is the fundamental basis for all these computational methods. And how do we assess that interactions? Okay, so we do virtual screening. So basically, we take thousands and millions of compounds, and then we just run it through computational software, and then we uh, score them based on their interactive energy. So that we have various tools and then various methods of molecular docking. And then we moved on to actually look at pharmacophore models, and then we looked on de novo design, identifying the binding site, and then we tried to design. Even we have what we call the fragment-based drug designs, and so on. Various methods are all there, but there is also one of the important parameters, or one of the important drawbacks, is that their correlation to the wet lab data. Okay, so that's the important thing. Okay, and this particular method, uh, tries to take that into account. Okay, so to address that. Okay, so that is why we call it as a quantitative structure activity relationship. Basically, we try to use the activity of the compounds and then their correlation with that, and then we quantify it. So we use some sort of quantification methods to find the correlation between the activity and then the structure. So obviously, we very well know that all the properties of a molecule, let's say that they take any chemical molecule, and then their biological properties, chemical properties, physical properties, electronical properties, everything depends on their structure. Okay, so that is one of the fundamental, hypothesis. Okay, so everything properties that are derived from the electronic arrangements or atomic positions and so on. So that means that the molecular structure, the electronic structure, everything plays a vital role in this. Okay, so that means that the structure is very important. The understanding of the structure is very important. Okay, so how do we correlate that structure with respect to the activity is what we are trying to, look at here. So basically what we intend to do is that QSAR refers to a group of techniques that aim to link molecular descriptors with biological activity through mathematical models. Okay, so so we have a set of compounds, and then we have their activities, and then we try to connect the activity of a particular molecule with its structure by the use of some mathematical models. Okay, so we try to correlate the activity and the models. In order to correlate the structures, so we use what we call it as a descriptors. So descriptors are, we cannot just simply use one as a structure alone. And then obviously we use various features, structural features of the molecule can be used. So we extract certain number of features from the molecule, and then we correlate the features to the activity. And then when the features, because obviously the activity are very much dependent on the features. So we collect a lot of descriptors, and then the descriptors, obviously what we see in the structure is that a visual aid, but now we're trying to get certain descriptors that can be quantitatively described, and then we calculate the activity, which is again a quantitative number, that is whether it is an IC50 value or efficacy or whatever. And then we correlate these two using various computational approach or mathematical approaches, basically mathematical, but then we use computers for that. So we use the traditional method is regression analysis. Okay. So basically what we're trying to do is, so activity of a molecule is a function of basically a function of the physicochemical properties or the structural and for the structural properties of a given molecule. So we just want to find out what is that function. So that is your QSAR, structure activity relationship. And then we, of course, we add some error. Okay. So this is what we intend to do. So what is the advantage of having a QSAR? Okay, so the one is the QSAR models are built, and then for three main reasons. One is to understand the relationship between uh, structure and the activity. So how does the structure correlates to the activity? And then the next is to design compounds with improved affinities, improved activities. And then the third one is to obviously predict the activity of your compound prior to their synthesis. Obviously, all these in silico methods, computational tools try to predict a lot of potential inhibitors or drug molecules, and then they try to we want to predict their activity of their compounds before we go ahead and synthesize these molecules, and then before we synthesize. Okay, so basically this is how the workflow is. So what the traditional method is that we have, lots of libraries, compound libraries, and then we get, compound, the physical actual compounds are all done by the pharma companies. They do an in vitro assays, high throughput assays, and then we also do large chemical libraries, and then we try to, do in silico screening and so on. We find the virtual screening, and then we get these in vitro assays, in vivo assays, and all these things happen. So that means that we get a lot of in vitro data. Okay, so once we have all these things, then we can start with the QSAR modeling. Okay, so which means that for the QSAR to work, we need a data set of compounds that and whose activity is known actually. Okay, so unless we know the activity, then we cannot develop the QSAR model. Now, given that we have so many databases and so many molecules are screened against a lot of targets, so we have a lot of experimental data that can be used for QSAR modeling. So, which is very important. So, once we have that QSAR model, experimental data, then we can use QSAR modeling, and that can be used to validate these models. Okay, so and then can be used to efficiently identify potential lead molecules, because once we do it is both these, starting with the library of, whether it is in vitro screening or in silico screening, we start with a random library of so many compounds, and we have a lot of work to do. But once we have something and then we have some data that we have activities known, then we extract information from these known or the evaluated compounds, and then use that knowledge to identify new compounds or select compounds that are more potent or more realistically, have activity. And we can use that information to improve the activity, and we can also try to use this information to evaluate a particular compound, whether it will have activity or not. Okay, so that's the point. So as I said, this QSAR model, it started in 1865 itself. So that is obviously in 1865, Crum, Brown, and Fraser, they suggested that obviously there is a relationship between activity and the chemical structure. And then it is improved, and then in 1969 it is properly took a form where Hansch he tried to correlate biological activities with the physicochemical features. And then later on, and again, now it is improved. And the current status we have, so 1D QSAR, 2D, 3D, and so on, multi-dimensional QSARs are all going on now. So what is different types of QSAR? Okay, so first, uh, zero dimension, that means that basically there's nothing, just the atoms. And then one dimension means using information that is only one dimensional number of atoms and so on. Then you have two-dimensional data information, and then three-dimensional information, and then we have four-dimensional, five-dimensional, six-dimensional, and so on. So basically, that what dimensionality means is that we start with the molecular descriptor. So what is a molecular descriptor? So basically, you have the molecular structure, and then there is a molecular property. And then the molecular descriptors are ones that actually we use to connect these two phenomenons. Okay, so they are the numerical values used to describe molecules' physical and chemical properties. Basically, for example, if you take saccharine, for example, this is 1D is just a molecular formula. So that means that a one-dimensional data means that just this is the only dimensional data. That means that it contains one nitrogen atom, and it contains molecular weight of 183. It has 3 oxygen atoms or 7 carbon atoms, molecular formula, atoms types. These are like one-dimensional data. So it means that it is only just basic atomic composition. Two-dimensional data means it includes, let's say, that the number of rings, hydrogen bond donors, hydrogen bond and so on. So like this, these things. And then three-dimension means that it uses three-dimensional interactions, that is, dipole moments and molecular volume, the surface area. So it is in the molecule is described in 3 dimensions. So like I said, these are every one of these value is called a descriptor. So for example, you have hydrogen bond acceptors, the number 3, number of rings are 2, and then hydrogen bond donors 1, and then rotatable bonds, that means that there is no free rotatable bond, degrees of freedom, that is again 0, like this. So each one of these information can be considered as one molecular descriptor. So we can say that a molecule should contain at least one nitrogen. Or you can say that a molecule that should contain at least a couple of oxygen atoms. Or you should say that molecule that contains 2 sets of hydrogen donors and 3 hydrogen acceptors, and so on. So likewise, that molecule should have certain number of molecular weights, and then molecule should have certain volume, certain surface area, and so on. So likewise, every one of them is a number, numerical value, which means that they all described can be used in an equation. And we can dissect. So for every molecule, we can have there is a numerous molecular descriptors, and the molecular descriptors can be decided. There can be so many different numbers, and we just have to use. So the number of descriptors that can be derived from molecule is virtually unlimited. We can just, need information to be converted into number, but only the problem is that the information should have some correlation, some type of correlation to the property that we are going to look at. So basically, virtually unlimited, that means that you can use any information that, correlates or, describes the structure, can be used as a descriptor, molecular descriptor. Okay, so for example, there is one program that uses 1612 descriptors, and they can be described into 20 categories. Okay, so that means that you can have, there's so many different descriptors. Okay, so the first, the mathematical correlation with respect to these is, you can start with what we call it as Hammett equation. Okay, so Hammett equation that all of us know, that basically it's an equation that correlates the the pKa values to these K naught equilibrium constants. So basically, we take simple organic compounds, let's say benzoic acid, and then calculate its dissociation equation. That actually this dissociation and its various attachments constitutes to its pKa value. That is the ability for it to donate the electron, donate the proton. Okay, so it is an acid, and the pKa value corresponds to the acidity, that is the efficiency of this level of this acidic nature. Okay, so that can be easily calculated. And Lewis Hammett, what he done is that he basically correlated the dissociation constant of aromatic acids influenced by the electronic properties of the substituents on the phenyl ring. So basically that when I attach a phenyl ring here, this is a benzoic acid, and then if I attach an electron donating or electron withdrawing group, basically they influence the acidity or the pKa values differently. Okay, so basically what he tries to do is we try to quantify that. So that is what we call it as the Hammett equation. And then he tried to plot the log K by K naught, that is the substituted benzoic acid versus the benzoic acid. Okay, and then he found out that it is actually when you change, when you plot the values, these different groups, and then they form a linear relationship as the ability to electron donate or withdraw increases, and then it actually excuse me, there was linear relationship. So from that, what he has done is he has developed a equation, that is log K by K naught is equal to rho into log K by K0. So it is given as log rho and sigma. Okay, so these two values can be calculated for every substituent. So every substituent had different specific values, and then what he has observed is that they are very characteristic, and from these values we can easily calculate the pKa values and so on. So basically what he has done is that he has expanded this to calculate the substituted benzoic acids, to calculate the correlation between the substituent nature and the acidity, that is the pKa values of this one. Okay, so that is the basis for this one. So where we can use the structural information and mathematically correlate it to a specific property of your molecule. So later on that there is two important analysis, that is free Wilson analysis and Hans analysis are these they are the early days of QSAR. So basically what they done is that free Wilson analysis, he used the lipophilicity of these equations, and basically what he has done is activity is equal to K1 into X1 plus K2 into X2 and then Kn and Xn plus Z. That is a constant representing overall X, and then Kn is an it's a constant, and then X1 X2 is the indicator value. Okay, so that means that basically what he has tried is to analyze everything. So basically identify descriptors and then use it to correlate with this one. So you have activity, and then activity can be derived as a function of various molecular descriptors and then something. So you have the molecular skeleton, that is you have this molecular skeleton, and then you calculate the molecular descriptors and then you can use it. Okay, so the problem with this one is it is computationally straightforward, which means that it is easy enough to do, but the predictions are only for the substituents that are already included. Okay, so that means that if I have to calculate, arrive at this equation, I need to have a lot of, the Hammett equation, I need to have the experimental data for similar structural information. Okay, so the substituted benzoic acid means that I have to calculate the acidity and the equilibrium constant for a lot of known standard substituted benzoic acid. Only then I will be able to get it. So it is a fairly similar approach. Okay, so the free variance analysis advantage is that no need for physiochemical constants or tables. So use of structures and unusual substituents. Okay, but the problem is that this one you need to have a lot of known compounds that have same molecular descriptor, similar type of interactions, similar type of molecules has to be there, and then you have to have these things. And again, this one is very difficult to rationalize whether particular this thing is, one is why a specific substituent has a good or bad activity. So we cannot, give a justification for why something is better than the other and so on, because it can only tell you that whether it has a good additive or not. So just again, you have to have standard set of values, and from that we can be able to calculate these things. Okay, so Hans analysis, basically he used additional information, more information, that is electronic characteristics, and then hydrophobicity and lipophilicity. So he used only the lipophilicity. In this one, he used additional parameters. So basically, it did give, this is the equation that we have, he has used, and then it did give, it is better than the free Wilson analysis. But however, again, it is the basis of everything. And then what he used is regression coefficients, regression analysis. So he used log P, and then electronic characteristics, that is Hammett electronic parameters, that is sigma, that is various electronic parameters, and then he used that. Okay, so that means that the results were better in this one. And these are the different types of molecular descriptors that again we will see later on. Some of these things: hydrophobic parameters, partition coefficient, log P, distribution coefficient, capacity factor, and then solubility parameter, Hammett constants, TAF's inductive constant, Swine-Lupin field parameters. There is lots and lots of parameters that has been used as a descriptor. Okay, so the descriptor, as I said, there is so many descriptors has been developed, and we can use any one of them. And again, the descriptors are obviously not all descriptors can be used at all the time. So the ideal scenario is that we have to use minimal set of descriptors and that actually not overlapping. For example, partition coefficient is a distribution coefficient, and log P value. So there are related coefficients. So that means that we have to be very careful. So for example, hydrogen bond donors and hydrogen bond acceptors are related. So that means that using both of them in the same equation is not advisable. Means that it is only increasing the the number of variables, but then it does not actually add additional information. So that means that the set of descriptors that we are going to use is going to be very selective. So you have to use unique descriptors, and those descriptors should have some correlation to the activity or the property that we are trying to understand. So that means that if you have, so you have to choose the descriptors carefully. Okay, so what is the general procedure for QSAR? So basically, and this is a generic. So the QSAR, depending upon what you know, there is no standardized protocols that can be used. So it depends on the set of depends on the receptor type and what type of QSAR that you want to do, why you want to do it, and what is the available data that you have. So based on that, you might have to modify the protocols, but generally what we want to use is, this is the generalized procedure. Okay, so what you can do is, first is that you have to select a set of molecule interacting with the same receptor with known activity. So that is the basic requirement, because as I said already, that we need to have the known structure and then activity data. So that means that we need to have a set of molecules that have interacting with the same receptor. Obviously, that receptor has to be a constant, and the activity is quantified. Okay, so that is the first step. That is the requirement, basic requirement, that where we can do a quantitative structure activity relationship. So that means that we should have experimental data with a known activity, that is IC50, EC50, or K values, that for certain set of compounds known for the same receptor. So now we have to use these data set. So they use the molecules and then identify the descriptors for that we want to use. Okay, so basically you can use 2D, 3D, and so on, depending upon the type of the molecule and your objective. We can try to come up with more number of descriptors. And then obviously that we are going to use two sets of data sets. One is for training and one is for testing. So use a small set of data to validate our QSAR hypothesis. And so you use, dissected small 10% of molecules, you keep it for testing, and then you have to use. So now you have to build a model that basically arrive at, analyze the descriptors and their correlation to the activity, and then arrive at a model that could correlate these things. Okay, so basically this build a model or analysis can be done in various methods. Okay, so basically it can be a regression or statistic method or machine learning approaches. So basically you can use the early examples, we used regression methods, and then later on we used more advanced statistical methods, and then nowadays even machine learning and artificial intelligence can be used to correlate them. All right, so the once you have a model and then test on the testing set, so you have this training set that is used to then generate the model, and then we can use the testing data set to test the model. Okay, and then you can use it to use the model to predict the activity for new molecules and then validate them and for improved activity. So we just, because these are the models that are trained and improved all the time, and these models are specific for a given target and the data set that we are using. Okay, so this is what we intended to use. Data analysis methods, as I said, we can use a regression method. That is the classic method that is already used. And then we can use either regression methods, and then we can use statistical methods, or basically all these recent methods, fuzzy networks, and so on, cluster analysis, principal component analysis, discriminant analysis, and so on. Okay, so usually statistical methods provides good data, but then given that we can do principal component analysis to identify which descriptors are clearly discriminating uh, the activity which has higher correlation, and then we can try to identify the features that are actually more reliable, and then we can try to rebuild the model and identify more proper data sets. Okay, so that way we can actually use various methods of the neural networks and so on. There are a lot of modern techniques that can be used, and we can also use cluster analysis and discriminant analysis. So basically cluster analysis is that because when you're trying to use these QSAR, usually it works better when you have a similar type of molecules. The training set uses, so when you try to use data that are from different types of molecules, that means that you have broader structural features, then it is very difficult to find the correlation. The convergence is difficult. So that means that we have to use cluster analysis. That means that we have to use molecules that have similar structural features that is easy for us to work. Okay. And also we have to make sure that we have some negative controls, means that we have molecules. Your initial data set should have some molecules that are inactive, or the activity range should have. You cannot have only molecules that have activity that are all active molecules. Okay, so this is pretty much what I said. It is just as a data sheet. So basically, you have a curated chemical data set, and then descriptor generation, split into training and test sets, and then you build a QSAR model. Okay, and then validation of the model, then virtual design of ligands, and then prediction of selected best ligands, and experiments to validate the compound. So this is basically a simple workflow that can be generally applied. So what I said earlier is this is just in a flowchart form. Okay, so the most important one is that selection and curation of the experimental data. Okay, so that's the first part that we have to select carefully. Okay, so first is the experimental data that we have to select, and then we have to clean. So we have to make sure that there is no obvious redundant data and other things, that we have to carefully remove them and then clean it. And then we have to arrive at the descriptors that we have to, identify descriptors, extract descriptors from the data set that can be used, and then mathematical techniques. Okay, so that means that we have to correlate the descriptors to the validated data, and then we have to use mathematical methods so that can be used, and obviously statistical criteria that we have to use to validate the equations. Okay, so basically what we need to do is, we have to first, when you select the descriptors, we have to select an initial set and try to normalize it. So basically, we have to use all the data and normalize the descriptors. Means that it covers the whole range. That means that when I said, you have to have a particular data set, that whether what is the requirement for a descriptor for an activity, for an active compound, and also for an inactive compound. So when you have both of them, the equation would be better refined. So the model will be better. Okay, so when you have only active compounds, it is not easy to do it. And then initially you select an initial set of descriptors and try to identify which ones are good, which ones have good correlation and which ones have bad correlation. And then you remove, and then you refine the set of descriptors, and then you try to use. Okay. And then effectively nowadays it's, obviously that we use machine learning method and so on. And again, we have to use training and test data set. Okay, so we use the training data set and then test it and the test data set. And we have to use cross validation. The validation is also important. Statistical validations are all good. Okay, so the problem that what we have is data selection is that congenericity problems. Basically, the first problem, as I said, is that the compounds should be of similar compounds. Okay, so what we have is a congenericity problem is that we have similar data sets. Usually when you screen, and most of them will have similar responses. So when you use a similar data set, it is difficult to train the models. Okay, so you also have to have negative data set. That means that the ones that does not have activity, and then sometimes you also need to have non-homogeneous data sets. Okay, so that means that data cleaning, that is first problem, data selection. Then data cleaning is similar experimental conditions, means that you should have all the experimental data. The activity measured should be on the similar experimental conditions. Means that if it is an assay, that means that assay conditions should be similar, because the activity varies based on the conditions. For example, if you're doing an IC50 value, that means that it is dependent on enzyme concentration and substrate concentration and so on. To a certain extent, you really have to pay attention to these experimental conditions, which means that using activity that are measured in two different conditions will not give you a good QSAR model. Okay, so that means that you have to use similar experimental conditions, and you cannot have duplicates. You have to do this thing. And then structure standardizations means that you need to have all structures in same orientation, and that would automatically be same structures may be measured twice and so on. And obviously mixtures, you have multiple ligands, the experimental conditions, they might have mixed with more than one ligand or other impurities present. So all these things needs to be taken care of. Okay, so data set curation is the crucial for any cheminformatics analysis. That means that the data set that we have, once we cleaned, then we need to see what are the compounds, type of compounds, and then how they are used. All these things we need to be data. So the data all should be in the similar format and similar, way. Everything, the activity units and everything should be in the standardized format. Okay, so that they all can be used. So that should be usable. So for example, the units, the structural descriptions, and the assay data, whatever the conditions, everything should be uniformly followed. Okay, so and then the next set is that we will try to split it between test and training data set. So we have to keep a small percentage of data as a test data set. That is something that we are already aware of. So which means that we have to keep a major part, that is 80 to 90% of the data should be used for training the model. That is your, to curate the model. And then to validate the model, we use these test data sets. Okay, so So how do we prepare the test data set? So test data set, you cannot just randomly take the 10%. The test data set should have all types of, we have to have all types of data. That means that you should have different uh, a different level of activity, so that because you cannot have all active compounds, there should be an active and inactive compound, so that because if all the 10% data is are all active compounds are all moderately active or something, then the prediction may not be actually the accuracy cannot be predicted. So that means that we have to actually make sure that we have samples that are kept for all types of activity. The one that is inactive, moderately active, and highly active, so that your model should be able to predict them correctly. So if you keep all of them are active, it may not be. It may not. The accuracy may not be actually predicted. Okay, so we are going to look at some examples for the descriptors. Obviously, uh, you know there are lots and lots of, as I said, that there is an unlimited number of descriptors, but the descriptor that we actually have choose should the most of these QSAR models that have comes with a lot of huge list of descriptors that we can actually select. And now our objective is to select the descriptor that is suitable for the data set. Okay, so if all the molecules are all lipophilic, that means that we don't have to worry about lipophilicity. If all the molecules have at least 4 or 5 hydrogen bonding donors, that means that we don't have to use that as a descriptor. If all the molecules have certain features in common, that descriptor is not useful, because that means that you all have the same thing. And there is also another thing is that you want to use the descriptors uh, that are not redundant. So, for example, a descriptor, for a particular characteristics of the molecule can also be used, can be described by more than one descriptor. So, we don't want to use those redundant descriptors unless we really have to look at this property. Okay, so that means that we really have to be very, very careful. And so the choice of descriptor is one of the important uh, you know thing, and that depends on the that actually validates the model. So if the choice of descriptors are poor, that means that the model may be an incomplete model. So because you're not using all the descriptors, all the information that is available, so that means that you have to use ways of selecting descriptors that actually describes the molecule. So again, there is no standard set of descriptors. Okay, these are the things that we have to use, and so on, because these set of descriptors that sometimes you have to vary based on the data set, that is a molecule set that you have. Okay, so that means that we may not have the actual, there is no standard set of selection. So that means that you have to really select the basic set of descriptors and then try to build the model, validate it, and then you try to retrain the model, train again, and so on. And then we have done these things. And again, you cannot use too many descriptors, means that you don't want to have too many descriptors. That again, that increases, it makes the model too complex, and that is not good. And again, you don't want to use too little. Okay, so it's like underfitting and overfitting. Okay, you just have to use a limited number of descriptors, and then try to get the best correlation. Okay. So basically, descriptors, you have measurable physical properties and calculated properties. So these are things that density, ionization energy, vaporization, molecular weight, hydration. These are all descriptors that can be used. Okay, and then these are quantum mechanical things, obviously homo energy, LUMO energy, polarizability, molecular volume, van der Waals surface area, molecular refractivity, and so on. These are all various calculated properties, electronic properties that can be used as descriptors. Okay, so there is a lot of other descriptors, constitutional descriptors, topological, geometrical, electrostatic, quantum chemical, quantum mechanical, molecular orbital, thermodynamic, DFT, and so on. So there is lots and lots of descriptors as I have here. So all these descriptors can be used to select uh, these things. And again, pharmacophore based descriptors can also be used. Uh, okay. So these are basically all these various properties uh, that can be used as descriptors. Okay, so that's I don't want to go into details about it. You can use it. Okay, so next is we can move on to the validation of the QSAR models. How do we actually validate? Okay, so first thing is internal validation. Simple cross validation. That means that we will see whether this particular model is valid, whether it is actually predicts, and then the training and test data test, and then using external validation, that is completely independent compound. That means that we can use. Uh, okay, and then these are the things that can be used, and basically, okay. So this is the study design for QSAR guided drug discovery program. So basically, what we have to do is electronic databases and then lab collection. That means that you have in-lab in-house data and then literature data. So then we use all of them, and then data collection, curation, integration, and then we create a data repository, and then we use a predictive QSR workflow. That means that we try to develop a model, and then we have the QSR model, and then we use the models, and then use the model to screen. And then once you identify the molecules, once you have this experimental validation, and then if it is good, then it goes back to the database to strengthen the database. And then if anything is, we can improve the models based on as the databases increases. So this goes in cycles. Okay, so that means that we can actually use it. Okay, so now there is obviously there is a lot of open source tools that are used. Okay, so QSAR applications, obviously it's used in drug design, and then toxicology predictions, ADMET predictions, and then environmental impact. So these are the main applications of the QSAR. Okay, so there are many open source tools that are available, online resources are available for QSAR. Okay, so there is also proprietary one. Schrodinger has a QSAR tool, and then but there is also plenty of open uh, tools that are available for QSAR. Okay, so this is pretty much what I had for QSAR. So it's a QSAR is a method that is highly specific, and we can use it for a specific target. And when you have a specific data set of compounds that have known activity, and we can develop a QSAR model, and we can use it to improve the efficiency, improve the predictability, and to actually get the use this information for the virtual screening. Okay, use this information and then select for the screening. Okay, so I'll stop here. So if you have any questions, I'll answer. And then I have my scholars who would do a demonstration of QSAR model building. Okay.
Is my screen is visible?
No, not visible.
Now?
Yes, started. Yes, now visible.
Okay. There are many available online tools are available to predict the QSR. Now I'm going to do a demonstration in ChemMaster, which is the ChemMaster is a chemoinformatics and drug design software which is specializing in a predictive QSR modeling. Here, this is a ChemMaster 1.3 Basic, which is a free source which is available to build and analyze a QSR modeling. You can download and predict and build the QSR model. Okay. This is a ChemMaster software page. Is my screen is visible? The software page is visible.
Yes.
Yes, ma'am.
Okay. Now, first step is we're going to import a model. We're going to import a data set. For that, we want to click a file option. Here, in the right side corner is available, the file option. And we want to import a structure. Okay, this is a predefined data set where the chemical structures were collected from PubChem, ChemDeable, and ChemDeal database as well as the relevant literature sources with known EC50 values. This is the data set which is containing 44 compounds that is active against the target muscarinic acetylcholine receptor M2. This is the receptor is one of the G protein coupled receptor to activate by an acetylcholine. Here, the target is muscarinic acetylcholine receptors, and they are active. The structures are active site by this target. Now we are going to do the. There are before starting. I want to explain the overflow of the QSR modeling. For this, the four steps is involved. First step is scaling up the biological activity. Next one is calculating the molecular descriptors. Third one is dividing the data set into training and test set. And fourth one is building and analyzing the QSR model. I am showing a 2D QSR. For that, first I am going to explain the first step, that is to scale the activity into a log scale.
Excuse me, ma'am.
Yes.
This screen is just stuck now.
Not struck. I will just explain the overflow. Now we're going to see about one by one. Okay. Now we're going to scale the activity. Why we want to scale the activity means here the EC50 value is mentioned. Here the EC50 value is wide range. To improve the model performance and linearity, we want to convert this data into a log scale. For that, we want to click. For that, we want to click table option. Is my if table option and add calculated column. From this, we want to convert the EC50 value into a log value. For that, we want to use one of the formula, that is PEC50 is equal to minus log into EC50. I am explain how to insert this formula in this added calculated column. For that, we want to first rename the column name as PEC50. The EC50 value is converted into log value. This activity is called P activity. For that, we want to give a name as PEC50 value. Now we're going to add the formula. For that, we add minus symbol is here, and add function. When we add function, the log 10 is available, and we want to add column EC50 because we want to convert the EC50 value into a log data. So we want to add column as an EC50, and then the EC50 unit is here. Everyone is shown that the value is in a nanomolar. The activity should be in a molar, so we want to multiply by 10 power minus 9 to convert a nanomolar into molar. For that, multiply and add constant. Here the double star is available, add constant. After that, the double star is available. This means the power symbol. After that, minus, and we want to add 9 and close the bracket. This is the formula which is used to convert EC50 value into PEC50 value. So click a calculate option. This is the one column is available, that is PEC50 value. Now we will convert the data into log scale activity. Now we're going to move a second step, that is adding a molecular descriptors, which is an important step in QSR modeling. For that we want to click calculate and click molecular descriptors. Here there is a molecular descriptors are available. What is descriptors means? Descriptors is numerically represents the chemical structures and capture the information such as hydrophobicity, molecular size, polarity, and topology. Here the ChemMaster is automatically calculate the wide range of 2D molecular descriptors. Now we going to filter some of the descriptors for our analysis. For that I click molecular weight. You know that the molecular weight is to determine the size of a compound, and another one is log P. Here the log P is a lipophility, the absorption, and a membrane permeability constant, and next one is rotatable bonds. We want to click these three. After that we want to click this left arrow and click OK. These are the molecular descriptors. Now we're going to select. Here the rotatable bonds, why we going to select means we want to calculate the molecular flexibility of the compound. So we use these three descriptors and click OK. Okay, now everyone will be show this extra three columns has been added, that is rotatable bonds, molecular weight, and log P. We want to check if is this available for all 44 compounds. Yes, it is available for all 44 compounds, rotatable bonds, molecular weight, and log B. And the next step we want to use means, that is we want to divide the set. Why we want to divide the set means we want to divide the set as training set and test set. What is training set means? Training set is used to build a QSR model, while the test set is to evaluate the predict the performance. Here to divide the section, we want to click QSAR and click divide data set. For that, here some of the option is available. For structure, we want to click all. Column name is set. The method is, there are so many methods used to divide the sets. For now, we want, there are three sets. That is, in ChemMaster, this division can be done by using random splitting and rational selection methods. That is typically around 70 to 80% of the data is used for training, and remaining 20 to 30% of the data is reserved for testing. Here, three methods is used commonly: K-means clustering, Kennard-Stone algorithm, and random. Now we want to going to use a Kennard-Stone algorithm, because this is the very common algorithm which is used to select the column descriptors. Now we want to click Kennard-Stone algorithm, and we want to click these values. Molecular weight, log P, rotatable bonds, we want to click this descriptors. Okay. Okay. Here this option is showing, right? The set option has test, training, test. Here why this option for different compounds has different test and training means, when the compound is set as a test, it is used to build the QSR model. When the compound is used to test a set, it is used to predict the performance. So next, this is the third step. We want to divide the test and training. And the next step is we want to build a model and analyze the model. For that, using the training data set, ChemMaster applies a statistical and machine learning algorithm to establish a relationship between descriptors That is descriptors means PEC 50, rotatable bonds and molecular weight. This is a descriptors. And then the biological activity. Biological activity is a PEC 50 because we want to we convert already EC50 into PEC 50. Now we want to give a relationship between this molecular descriptors and PEC 50. For that, we want to click QSAR and build model. Here, first one is XY variable. Here, what is XY variable means? Which one has been in X and which one has been in Y. For that, we want to click Y variable as a PEC50. And then we want to click a molecular descriptors, that is molecular weight, log P, rotatable bonds, and click OK. Before that, we want to add some of the things in build model. So again, we want to click build models, PEC50. We want to click molecular weight, log P, rotatable bonds. Okay. Next one is dataset division. Here, what is dataset division means? To build a model by randomly, but we have already we have already divided the section into training set and data set. So now we want to click column. After you click column, this session will be available, that is division column, training set label and test set label. From the division set column, we want to click set. After that, training set, we want to click training. For test set label, we want to click test. Next, we want to adjust the model setting. Here, the model name is QSR model 2. We want to click any model as a model name. And X variable pre-processing is, there is two options, that is standardize and scale 0 to 1. Here, we use standardize. You also use a scale for your experiment and like 0 to 1 and 0 to 2, that is a scale option. Next, future selection, we want to apply a variance threshold as a value as 0.001. And here the method. This is a machine learning method which is used by Chem Master to analyze the QSR model. Here some of the machine learning method is used. Now we going to use a method that is MLR. Here MLR, what does mean MLR means multiple linear regression. This is very simple and popular method to calculate and predict the model. So we want to click MLR. Next, we want to compute Q square, CV and LLO. What is Q square? LLV. LLV means here the what is Q square means? Q square predict the ability of the model using cross validation. Here, what is LLO means? Specified leave one out. What is leave one out means? One sample is removed and model is built and another sample is predicted. Like by one is removed and all the sample has been predicted. That is LOO. Now we're going to do click OK. Here we have the results. This is the results. Uh, mm. Here what is R square represents means R square R square represents the coefficient of determination. It should be points. It should be above 0.7. That is a very preferred value for the training and test. Here, next one is RMC. RMC means prediction error on the data set. Here, MAE and Q square. Q square value is higher than 0.5. This is necessary for the model should be a good predictive model. So always the Q square is higher than the 0.5. If the Q square value is less than the 0.5, the model cannot be considered as a good model. So here we have the value q square as a point above 0.6. So the model is the model is a good predictor model. This is the model feature, and this is the equation which is used by the ChemMaster software, that is a MLR, multiple linear regression method, to calculate and analyze the model. Here, this is the graph. Here, what is in x-axis means predicted by our QSAR model. And here, PEC50 value was an PEC50 value is an activity value. I already told that why we want to build the model means we want to compare the relationship between our QSAR model and PEC50. So we want to do a linear graph that this is the graph which is represent. Here what is blue dot means, the blue dots are representing the training set and red dots are representing the test set. Here what is the line is represent means ideal line, which is the which is used to determine our model is good or not. If the line is aligned in the point, so if our model is very good, that is the prediction is equal to an experiment. If the point does not align the line, we want to do again, because that is not a good model. So this is the results which is built by a chem master and QSR model. With that conclusion, the QSR 3D QSR will be continued by my fellow scholar Zarina.
Can you share this tool, Chem Master Basic 1.3?
Yes, I will share that too.
Just share the tool so that like they.
Okay, 1 minute. This is the ChemMaster website. Here, the ChemMaster 1.3 basic is available as a free.
So that they can download. Yeah.
Yes, here we
No,
want.
but it is not download. It is just share the 1.3 version. Yeah, it is creating a problem.
Am I audible?
Yeah.
Yes. I'm going to share about 3D QSR. Let me share my screen. Can you able to see the screen? Yes. Okay. Let's start. I think Priyanka explained about 2D QSR. What I'm going to explain is about 3D QSAR, and I'm going to show that using Mastro interface, which is Schrodinger. So before starting with the Schrodinger interface, I will show where you get the data sets from. So usually the data sets is in the form of .stf files. So you get that from either binding DB database. So where you can just search the target protein name or by the compound name or anything else, or the author or article title. So I will just search using the target name, which is muscarinic acetylcholine receptor. So if you just click go, and you can get the data set, and what the target protein I aim is for the M2, receptor M2. So if I click on that particular target name, you can get this page. So you can see there are so many ligands. So you can just make a data set out of that. So I'm just going to add this page along and then going to make a data set. So after that, it will ask you whether you are going with a 2D file or 3D file. So for the QSIR, for doing QSIR, you have to do it with 3D file. So you have to click on 3D and then just click on go. And this website will ask you for login name. So you have to just give the mail ID and the password. If you have an account already, you can type the password or you can register here. Oh, wait. So after you log in, you can just give submit and then you can download the SDF files, what you have selected. And since I already downloaded the files, it's already in my directory. So I'm just going to show you how to import the structures into the master interface. So this is not only the a database available for downloading the datasets. You can also get it from Pumpkin too. If you search by any like a name or the compound name, you can directly get into the 2D structure and the 3D conformance of the same we can. And you can download the SDF file format here. So since we use 3D format, you can download it from the 3D conformer as SDF file. And now we are moving into Mastro interface. So I've already imported the structure, but I will show you how to import the structures first. So before proceeding with the project, you have to change the working directory. I've already changed the directory to my where I want to save my files. So you can just move into the place where you want to save the files. And now you can choose that and you can come back. And after you choose the directory where want to save the files, you have to import the structures. So now you can import the structures where you have saved the data set. So now I'm having the data sets here. I have already imported the structures into the master interface. So you can just click that and you can just select that and just give open. So it will be opened in the interface there. So now I already have the data sets here. So I've already imported the structures here. So it will show you like this. And now after importing the structures, if you have successfully imported, you can see that in the project table after selecting that. So the first step in 3D QSAR is that you have to prepare the ligands which you have imported. So you can do that using two ways. So one is you have to go to the task. So before going to the task, you have to select all the entries which you have imported. So after selecting that, you have to go to task and browse. You can see like you can see various other options or like you can just search for leg prep. So you can find the leg prep here. So you can click that leg prep and the entries are selected already. The project table entries are 44 numbers, so it's already there. So I'm just leaving it as it is. And all other things, you have to select on neutralize option. You have to check in that. And you don't need to have tautomers for this. So you just deselect for the generate tautomers option and you have to select the determine chiralities from 3D structure so that you won't have any duplicates. If there is any tautomers or like the repetitions of the one similar structure, it will neglect all those things and give you the single clean structure of one ligand. And you have to check in the Mastro output format, and then you can name this as any job name. So since I've already done that, it's showing me a different name, and you can give any sort of name. And make sure that the job is run in the 32 localhost, and you can just click on run. So all of the ligands that you have imported will be prepared now after giving the run. So since I've already prepared, I can show you, like, these are the prepared ligand prep structures, which I, after preparing the ligands, we can see that in the selection space. So after preparing the ligands, and you can select that for the next process. So before doing that, I will show the other option which you can do. So this is not only the way you can prepare the ligands, there is another way to do that, which is macro model. So the macro model will also prepare the ligands for QSAR. So when you select on this macro model, you can navigate to this minimization. So where you can prepare the ligands for this QSAR. So when you click on that, you already have the entries selected here, and you can leave all other options as default and then just give run, so that your ligands are getting prepared for the QSAR. And then these are the two ways to prepare your ligands or compounds for QSAR analysis. And the second step which you have to do is define the test set and the train set. So the data set which I am using is already a predefined data set where I all it's already defined like the training and the test set. So so I'm not going to deep into that. I'll just show you how to do that. And after you prepare the ligands, and if and yeah, there is this window option where you can see the entries you have prepared in the workspace, and you can see that my data set is already divided into test and training set, and it has log p values and molecular weight PEC 50 values. And if you want to calculate the PEC 50 value, there is a formula like 9 minus log 10 of this EC50 nanomolar concentration. So if you want to do the calculation, you can also do that using the data option, where you can go to the add property and then click on the from equation, where you can insert the equation and then calculate the PEC50 values for those EC50 concentrations. So then you will get this PCE50 values from the log. And to tell it in a simpler terms, it's just the logarithmic scale values of this EC50. So after getting the PEC50 values, you can just navigate like since your ligands is prepared, then you can move to the alignment. So when you see the ligands one by one, so it's in a different like you have to align in order to do the QSAR. So to do the alignment, you have to go to the task, just type align. So now you want ligand alignment. So select this ligand alignment, and I've already selected this project table entries, and now you have to check whether this automatic is checked in or not. So after checking all these things, you have to give run, and you will get the entries like this. So since I've already ran this program, it's saved here. So this is how you get after aligning all your ligands. It will give you like this. So if I click every entries one by one, you can see all the structures are aligned about the other. So this is how you align. Since these entries are like of different parietal backbones, they are not in a proper alignment even after aligning all the ligands. So after doing this alignments, you have to run QASR. So QSAR, in order to run it, we have to go to task and just type field-based QSR. Before proceeding to field-based QSR, I have to explain about the two types of 3D QSAR. So there are two types in 3D QSAR. One is the atom-based QSAR and the field-based QSAR. So in the atom-based, the molecules are treated as spheres and categorized as any one of the following, like hydrogen bond donor or hydrophobic non-polar or like negative ionic or positive ionic or electron withdrawing or hydrogen bond acceptor or submiscellaneous. So either one of them is categorized or it doesn't give you the whole picture. It will give you only the hydrogen bond donor, either hydrogen bond donor or the hydrophobic region or the negative ionic region. It will define only one of them. So whereas the field-based QSAR will give you the steric as well as the electrostatic fields. It will evaluate at the grid points surrounding the ligand using the steric and the electrostatic fields. And there is another type in this field-based QSAR. One is the force field-based QSAR, and the another one is the Gaussian-based method. So the recommended method for doing this QSAR model is the Gaussian method because it can give you the property-based fields. So where the Gaussian function, it will build the model using the Gaussian function and it will give the distance between the grid point and the atom. And it will also include the steric, electrostatic, hydrophobic, and hydrogen bond accepted hydrogen bond donor. Everything will be included in the very same field-based QSAR. So when you click on this field-based QSAR, you can see this window appearing. So after this, you have to select the entry. Since the project, let me check whether I have selected the particular entries. So you have to select the aligned ligands first and then go to task and then you have to select the field-based QSAR. And from this, you have to select this option and where you can see the aligned ligands is already selected. And in the activity, while choosing the activity property, you should select the activity and from this choose QSAR set property, you have to select reference structure. And you can click OK. And then the data set will be analyzed and it will be appearing on this field-based QSAR. And for my data set, it's already predefined as the test and the training set. So this field-based QSAR can't detect the input which I'm giving. So I will show you the other data set. So when you click on the activity and reference structure and then click here, it will be uploaded into the table of this field QSAR. And now you have to set the random training set as 70%. You can also give it as 65 or 80 or whatever the number, but the universal random training set percent will be is always 70%. So when you give the 70% and you click on apply, you can see that the data set will be differentiated or divided as training and test set. And after that, and when you give apply, you can see that each ligand is being divided into the test and the training set. And after which you have to select, then you have to click on this build model. So when it gives select this build option, you will get this pop-up. So when you are building the field-based model, you have to give the Gaussian method to build the model. So which is the recommended method for that. And your other options are default. And the other thing which you have to change is the maximum PLS factor, which should not be more than uh, 8. So if you are giving 5, you can also give it as 5 or 6, but 4 is the like if you are satisfied with 4 repetitions or the regression values, you can just give 4, and the others are left as default. And the number of ligands to leave out for cross validation, which should be always 1, and then you have to click on OK. And when you click on OK, it will generate the test results, and this QSAR statistics will be shown on the screen. Like, there will be also displaying the field fractions, where you can see the all of the numbers here, and the standard deviation mentioned here should be as less as possible. So 0.3 and 0.2 is a very good numbers for this data set. And while you are doing with your own ligand molecules or the data set which you have, you may not get the standard deviation as less as this. So it can vary up to 5 or like 0.6 or 0.7 like that also. But it doesn't matter, but you can get such values also. So the better, the less as the better it is. Like if you get a minimum or like the very least standard deviation, it's better for you. And all other values they have displayed is the statistics for the data set which you have imported into that. And you can also see the p-values for that data set, and this is the RMSE and the fractile scores, and the Pearson coefficient values is also displayed here. And from the standard deviation till the p-value, it is for the training set values. From the RMSE to the Pearson coefficient values, it is for the test sets. These values belong to the test set, and these values are for the training set. And you can see, you can also see this Gaussian, steric Gaussian, electrostatic Gaussian, hydrophobic. These are the scores given to the corresponding ligands. And after building the model, you can also visualize your QSAR model using this QSAR visualization. So when you click on this, you can visualize where the steric region is present or the electrostatic region is present. You can visualize the all those regions using this option. So there is this two options. You can click on any of the options to visualize the corresponding regions. And you can also see that you can also vary the contour color, and you can also change the colors of the contour also. And if you are giving the you can vary that. You can also see the field intensity, and you can also vary the positive saturation and also the negative saturation values. And you can see this, they have selected the Gaussian steric region, and you can see that in the yellow color. And you can also view the other types of regions like hydrogen bond acceptor, hydrogen bond donor. You can just click on the respective regions, and then you can visualize that in the workspace. And there is another option. When you click on the view field intensity from Gaussian steric, it will show the Gaussian steric region of the selected molecules. So you can also download the image from the workspace using the you can click on the workspace, save image as, and then you can save the file name as any whatever you want, and then you can save the image for your publications too. And so far, we have seen only for this test set data and the training set data. What if you have specific molecules that you want to test? Like you say you have designed a ligand or designed a ligand to target on a particular protein. You want to take it for the that drug discovery process, or you have to move it for the clinical trial. Then you have to do an analysis before whether this ligand is really effective in binding and really effective for to proceed with. And to do that, you have to predict whether this will be as effective as the molecules present in the market already. So we have already evaluated using the training and the test set data, and now we are going to do it with the unknown molecules, which we are yet to prove that these molecules are also effective in getting into the market. So to do that, you can import all those molecules, just like what I've said previously. You can import the structures of your unknown molecules like this, and you have to select all those entries. And you can just give the selected entries from this field QSAR, and then choose it, and it will appear in this screen. And then you have to do the prediction, and it will give you the predicted activity 1, 2, 3, and 4, because the PLS was set to 4, and it will do the runs for four times. And this is how you get the predicted activity values for the unknown molecules also. So you can get the values, you can get the biological activities. The numbers you can see here, right? They are the biological activities for the unknown molecules. And this is how you can visualize the structures of the unknown molecules using the visualization tool. I can show it in the master interface also. So now you can see click on the plus option, and you can see it in the tile view also. So since I have selected all of them, it's showing like aligned in an aligned manner. So if I just click on the phone on this, it will just give me on the tile view. So this is how you can visualize all of your ligands in the 3D structure. And I hope this will sum up all the 3D QSAR modeling and the analysis part. Thank you.
Okay, thank you, Jarina. So finished?
Yes, sir. Yes, sir. I've completed.